understand type conversions in C++. So let's take an example here. We have an int that is brace initialized, and then we have a double that is also brace initialized using that same int. And now we want to print out the value of the double. So let's compile. Is this going to work, or is it going to throw an error? You have to guess. Okay, it throws an error. So now let's investigate. Why are we getting this error that says cannot narrow from type int to double? Okay, so the keyword here is narrow. Alright, so what's happening is that with brace initialization, this is called list initialization C++, and it's very strict over here. So when we try to list initialize a double using an int, it does not allow narrowing because we could potentially lose information, so it doesn't allow this, so it throws an error, as you can see down here. So we can overcome this by using assignment initialization, which is more permissive, and it does not complain when you do narrowing. So let's do this. See how it compiles successfully, because even though there's narrowing occurring here, it doesn't complain about it. Alright. So for the rest of the demo, let's stick to using assignment initialization so we don't get errors because of narrowing. Okay, now let's talk about a slightly different type conversion, which is called promotion. Okay, like you get promoted, it's called promotion. Okay, so we have a short called small, and then we have auto sum small plus 1, and then we want to print out what type sum gets assigned to. So here we have sum, auto sum, so we don't know what type it is yet, and it's a short being added to an int. So what do you think you get when you add a short to an int? What is the type of sum? So type ID sum. What do we think the type of sum is going to be? Well, it's an int, because when you add a short to an int, you get an int. Why is that? It's because types smaller than int, such as short, usually get promoted to int first. So small plus 1 becomes an int expression. And here I'm just printing out the type name to prove it. When it says here I, that's for int down there. That could vary by whatever compiler you're using, but that's not a big deal. Okay, so now let's look at another example. So we have double pi-ish. Okay, and then we have a narrowing right now that's going to happen. We're going to narrow the double to an int. So we have an int called chopped, and we statically cast the double to an int. Okay, and let's print out chopped to see what we get. Okay, so is this gonna work or no? Let's see. Yes, it works fine. And chopped has a value of 3. So why does it work fine even though we're narrowing a double to an int? It works fine because of the fact that we're statically casting. So this is called an explicit narrowing. Explicit narrowing. And what makes it explicit is the fact that we have a static cast here. So we tell the compiler, yes, we know we're narrowing a double to an int, but we explicitly are doing that. So this tells that like, yeah, we know what we're doing. All right, so let's look at another example. So let's say we have auto mix, and then we want to print out what the type of mix is. So score is an int, right? You can see it up here. Score is an int, and you're adding it to a double. So what do you think the type of mix will be? Okay. Okay, so mix has a type of D, which is double. So now this is the usual arithmetic conversion. So when when types differ inside an expression, C++ converts to a common type. So here score is an int, but 0.25 is a double. So actually score gets converted to a double, and the whole expression becomes double. So let's do another example now. So here, let me just modify the out so that it prints out false and true instead of 0 and 1. Alright. So here's an example where we're subtracting an unsigned int. Basically, we're mixing signed and unsigned in this example. So you get a lot of surprises when you mix signed and unsigned together. So when you see a U, that means it's unsigned, so it can't go negative, and it wraps around the max value back to 0. And signed can go negative. That's the point of signed. Okay, so in unsigned math, you can't represent negative values, so it wraps around. And -3. Let's actually just run it to see what we get. You can guess right now. This is a good time to guess what you're gonna get. Okay, so for 5 unsigned minus 12, we get this huge number. Why? Because it's actually like -7, but there's no such thing as -7 in unsigned. So it goes to the max value and then it minuses 7 from that. So this is just the max value, -7. And you would expect -3 to be smaller than 5, but it's saying false. Why would this be saying that? Because this gets converted to an unsigned, which is like this huge number -3. So this huge number -3 is not smaller than 5 unsigned. So that's how it does it. Alright, so now let's look at a different example. So let's say we have int x equals 10, int y equals 4. And then we have double d equals x divided by 4, so 10 divided by 4. And now we want to print out the value of d. So what do you think 10 divided by 4 is? If x is 10 and it's an int, and y is 10 and an int, so int 10 divided by 4 int. What's the resulting double? Well, we already know it's basically either going to be 2 or 2.5 depending on how the type conversion happens. So let's look at what happens. Oh, there we go, it's 2. So this line surprises some people. So even though d is a double, the division happens first. That's the key thing, the division happens first. Since this is an int and this is an int, so both operands to the division operator are both ints, it's integer division. So first it becomes 2 as an int, and then it gets converted through narrowing to a double. So 2 stays as 2. But it goes from 2 as an int to 2 as a double after the division. Because just look at what it is. The operator's division and the operands are both ints. So the result is obviously not going to just be a double. That would never happen. But then after the assignment, it changes to a double. Okay. So let's say we want to actually fix this division. So how could we fix it? Okay, let's say we do this right here. Let's say we do static cast x. So here, we actually cast one of the operands of the division operator to a double. So one of our operands is a double and the other is an int. So in fact, this will be, let me just get the print here so that we can see the result. Alright, so this will be a double and this will be an int. So you have an operator operating on two operands. One's a double and one's an int. So what do you think the output's going to be? Yep, so it's 2.5. So what happened is that the entire expression now becomes floating point math. So we get 2.5. And this is the most practical use, actually, of static cast, forcing the expression to use the type that we intended. Okay, so let's talk about C-style casting now. So C-style casting looks like this. So we're casting to a double. So it's the same as this, but instead of static cast, you have double. But the problem is it actually looks simple, but it's really not. It's actually much more explicit and easier to use static cast, although it's counterintuitive. You'd think just casting like this is simpler, but it's really not simpler. It goes through very complex logic compared to this static cast, although it's C style. Like I said, it's not simpler. It's actually really complex, and you should avoid it because this is much easier to think through the behavior of. Okay, so let's look at one more example here. Let's say we have car C equals A, and now we just print out the value of the character. Okay. And now we statically cast the character to an int. So here we obviously know it's going to print out A, but what do you think here it's going to print out? Okay, so this prints out A, and this prints out 97. So this is casting it as an int, casting the car as an int. So the ASCII equivalent is 97. Obviously everyone already knows that. Okay, so let's look at another example. Okay, so we have int I equals 48. So here we're explicitly narrowing the int to a character because the character can hold less information. It's narrower. An int is wider. It has more bytes than a car. So this is called explicit narrowing. Here, let's put a comment. Explicit narrowing. And so let's print this out and see what the result here is. Actually, before we print this, let's just keep going with the example. Okay, so here's what I added so far. So we have int I equals 48, and then character 3, explicitly narrowing. Then we print out the car. It's just gonna be whatever the 48 is. I think that's like I can't remember what letter that is or what number. I don't even think it's a letter. And then here we have static cast double x divided by y. And here we have unsigned car UC A, and then we statically cast to an unsigned int. So let's see the result. So basically the point of all this is that when you have int to car, you can lose data, and you can make it explicit with static cast car, like we already saw from double to int. And also notice that the static cast double of x and double of x both convert a temporary value. So basically in this demo we're just standardizing on static cast because it clearly communicates intent to the compiler. That it's a conversion, not just a different looking expression. So that's it for today.